Okay, which is actually good timing because now we switch to the real topic, which is not yet, but the one part of it is actually the open source reconstruction framework that we used in this cardiac fingerprinting sequence or project, but also now for the MR6. So at PTB a couple of years ago, so apparently summer 23, we decided to create our own open source reconstruction framework for MRI. And the special thing is that we decided to implement everything in PyTorch. So everything is PyTorch based so that we are compatible with all the deep learning stuff that we do in our own group, but also, of course, want to provide it to other groups. And we can make use of the GPU acceleration that is intrinsic available in PyTorch. Because we use a lot of Pulseq, we also made sure that we have a full support for Pulseq. So basically, we have our own trajectory calculators for Pulseq. So you can just read in the sec file together with your raw data, usually in ISMM RD format, but also direct DICOM import that we support. And then this works like hand in hand. And special thing here is like a very advanced continuous integration pipeline, very high test coverage. So the unit testing 92% here, some additional tests. So this is really, we try to have like a more professional software implementation than it's maybe usual for science. And so this part or this reconstruction framework is what we also use in this MRSec framework now. So this is what we present today. So basically MRSec is our own repository for open source Pulseq sequences with a strong focus on quantitative MRI, like T1, T2, T2 star, T1 row, and also like fingerprinting that I just mentioned. Different trajectories, Cartesian, non-Cartesian. And the special thing is actually that in our framework, we not only include the sequences itself and the unit tests, but also we have an additional step where we simulate our sequences with MR0. So Moritz is also here, and I'm pretty sure we will hear much more about MR0 in one of the upcoming meetings. But this allows you, basically, it's like a virtual MRI scanner, which allows us to simulate this acquisition, and then we can export it as ISMM RD, import it again in MR Pro, reconstruct the images, and then have a direct comparison between the ground truth data and our results. And especially in quantitative MRI, where we get quantitative results, this is very useful. And a good quality check. So we actually also still found some minor errors in our sequences that we were sure that were 100% accurate. So also for us, it's still already a very good result. Okay, so I think we can continue. Just a few details, not supposed to understand everything that is here. So we plan to do it in a very modular way. So you have reusable parts that you can use in all the different sequences. One thing is, for example, different prep parts. So starting with composite refocusing blocks consisting of like 90, 180, 90 blocks, but also T2 prep, this MLIF4 style T2 preparation, which together with a composite block totals in like 27 different RF pulses used for T2 preparation, T1 raw preparation, inversion recovery using adiabatic pulses and everything in these predefined blocks that you can use over and over again. And as you can see in this code snippets, everything is typed, everything is documented. So we try to keep the quality extremely high here. So if we go to the next slide, one special thing that we also have is that we actually create an ISMM RD file together with all the sequences with some additional header information. So unfortunately, we still have the problem that some of the parameters that we get from at least Siemens scanners are not correct. So we correct or put all this information in a header file. And also, especially for non-Cartesian trajectories, we also add the trajectory information directly to this MRD file. And then also in the framework, we provide a function that allows you to combine the measured data from your scanner in MRD format with this predefined header file, basically brings in the trajectory information and corrects some of the other information so that you have everything in one file. And then in MR Pro, we can, for example, also use the trajectory information from the MRD file directly. And the next thing that might be a bit special, so we decided to include noise samples in all our sequences. if you're not interested, if you don't use them for like pre-binding at the end in your script, I mean, you can just ignore them, but I think it's a good practice to have it. And so we decided to put it here also not for sure together with the MRD information, so that basically also the scanner and your post-processing framework will know what to do with these scans. And I think, yeah, one of the last things, I mean, labels, I think more and more people use it. I can highly recommend it. It's fantastic to see what is actually possible if you use the correct labels in the correct way, with like ramp sampling and oversampling and partial Fourier reconstructions working in the ICE framework directly at the scanner. So I can highly recommend it, and for sure also for our reconstruction framework, it's not mandatory. We can still do it retrospectively, but we also make use of all these labels that are set in the MRD file, and it definitely simplifies your post processing. And yeah, I think with that, I will hand over to Christoph, who will talk a little bit more about some examples and some special focus on the quality control that we implemented.
Yeah, as Patrick already mentioned, we tried to look at the full pipeline, so also at the simulation of the sequence and the reconstruction. The main motivation for that was that we decided to have all these different sequences and multiple people working on that, and it was very difficult to actually, whenever there is kind of a pull request in order to update the code, make sure that everything is still working how you think it's working. And always having to go to the scanner, run all the sequences, doing comparisons to reference sequences is quite cumbersome. And so we tried it out with MR0, and that worked really nicely because MR0 is a full simulation package which takes Pulseq as input. So here we can basically, with MR0, create a phantom. We can create our sequence, our Pulseq sequence. We can then import the Seg file into MR0 and then run the simulation and then export it to ISMRD. So just basically 3 lines of code. And this 4th line here, this combined ISMRD, this is what Patrick also mentioned, right? That we write kind of additional information, which we know also the scanner is not correctly in the raw data file. We write that in a kind of empty raw data file, and then we combine it here with the acquired data. In this case, we combine it with the simulated data, such that all the information is in our raw data file for the reconstruction. And then we can do the reconstruction, and basically, because it's a numerical simulation, we know the ground truth, which means we can compare that. So here's an example. So again, just a transversal slice through the brain. Right here on the left-hand side, you always have the MR0 simulation. And in this case, it's a flash sequence. So we just basically simulated using the analytical flash formula what the contrast should look like for a given repetition time, echo time, and flip angle. And here's the reconstruction then with the Seg file. And here's the difference. This is scaled to 10%, right? So this min-max here is 10% of the actual one. So we get very good agreement for a radial, even for a spiral sequence with the actual ground truth. And this is all done automatically. So whenever we do a PR, we have an automatic script which then runs all through these examples here and verifies that the overall error then is below a threshold, and only then could you actually merge something into the code base. Here's another example, which is actually even easier if we do really quantitative imaging. So here it's a standard inversion recover single line spin echo reference sequence. And here you have the input T1 map, and here's the reconstructed T1 map, and you can see here it's basically a perfect match. In this case, of course, it's easier because we can directly compare back to the input quantitative parameters. We also have some other, like a Molly sequence. This is actually not now compared to a simulation here. This is a bit more challenging. Here we compare it to a Siemens Molly. And here we also based it a lot on what Rita Nunes did in the open Molly, in order to also have something for the cardiac imaging. So there's a big focus in our group. Another important aspect for us is what Patrick mentioned, is non-Cartesian. So here is spiral TSE sequence. We have a Cartesian TSE sequence, which we use for T2 mapping, and here the spiral version. You can also see a very good agreement with that. This is again now measured on the scanner. And here the special thing about the spiral is that we have this double spiral thing. So one color here is one readout, right? So we have a spiral in and spiral out is one readout. And here we struggled for a long time to get this implemented robustly. And so in the end, we basically we based our code on what Brian Hargraves developed quite some time ago on the VDS implementation, so the variable density spiral. But we wrote some wrappers around that such that it's a little bit easier to use them, and especially easier in the sense that you don't just get then the spiral trajectory, but the full block of your readout. So our function basically gives you one block, which is in this case the prewinder, the spiral in, and the spiral out, and then the rewinder again, and the ADC and everything centered to the correct timing. So you don't have to put the spiral together from all these individual blocks, but you get one basically spiral readout block, which you can add to your sequence in a very modular way. Here another example from T2 star mapping. So at the top here, it's a multi-echo gradient sequence for T2 star. Again, very good agreement. And the nice thing now is, right, with MR0, you can also then see what happens if things are not so great, right? This is now with a perfect B0 map field, and this is now with some B0 inhomogeneities, and you see exactly then these areas here where the B field is not is varying. You can also get then an underestimation of your T2 start time, for example. So it's also quite good in order to analyze how robust your sequence is to certain aspects. All of that is in the documentation. So all these things which I showed you are part of Jupyter notebooks, which are then, as I mentioned, run automatically. But of course, you can also have a look at them and click through and run them yourself in order to test these things. And so in the end, what we basically have is the nice thing is we have, for example, here a TSE sequence. Our basic workhorse of scanner is a Siemens scanner, where we then put Pulseq in and can do the reconstruction of MR Pro. We also have an open source low field system, which is part of a new project we're currently working on. Again, we can put Pulseq in, we get ISOMD out, we can put it to the same reconstruction. And now we also have the simulation, which we then allows us to compare it to some ground truth. So by using kind of Pulseq as our main sequence format and ISOMD as our main data format, we can now basically exchange whatever happens here in the middle for easy end-to-end MRI applications. So currently, this is roughly what we have in MRSec at the moment. So some non-Cartesian readouts for Flash, different relaxometry, quantitative maps, and then there are some other things which are currently we're currently working on and will be there soon. So just keep checking the repository. This already brings me to the end. So if you want to have a look at that, is the MRSec. Here is the MR Pro link, and this is just another link to our open source MRI scanner, which we are working on. So thank you very much, and I'm happy to take any questions.
Thanks so much. That was really, really helpful. Any questions or comments?
Yeah, this is amazing. Are there publications describing some of these? Maybe they're still in the process.
Yeah, so the publication what Patrick already mentioned, right, is about the cardiac fingerprinting, which we did. This has been published in Magma. About the whole pipeline, we haven't done that yet, no.
So I guess this is a comment and a question. So, you know, this is wonderful having this complete framework for simulation and validation, as well as, you know, the steps forward to multi-vendor harmonization. One part I guess I wanted to ask a question about is tools to translate vendor sequences into Pulseq for simulation, or, you know, how do we kind of move the vendor sequence into this framework, and is there any interest in it?
I mean, in order to be able to compare kind of what the vendor results, how the vendor results compare to, for example, a Pulseq implementation.
Well, I guess one way to think about it is Pulseq might have to be stretched to be able to do it, at least for simulation. You know, basically, we're talking about a vendor neutral representation that's suitable for simulation, as opposed to just having to somehow stick the, well, I guess maybe you could just stick the vendor waveforms in there, but things like that.
Yeah, I mean, for us, the simulation, right, is kind of a quality control tool in the sense that we want to make sure that when we make changes to the code, we don't break anything, and that at least if everything is perfect, we should get the correct quantification. But as far as I know, but maybe Moritz can comment on that himself, there are ways of also getting non-Pulseq sequences into the simulation framework, such as like MR0. Don't know if Moritz wants to comment on that.
Hi, can you hear me?
Yep, we can.
Sorry, I was not prepared to really participate here, but
Sorry for that.
well, in principle, well, I think the vendors also have own simulations, most of them, right? So they also send their streams to built-in simulations that they use. I heard the new IDEA version from Siemens that you can actually in IDEA also call a simulation. So they do this, and of course you could switch to another simulator, but yeah, so I don't know if that answers your question, but of course it's possible to somehow go closer to each vendor, yeah. But better would be that the vendors have kind of a format that they agree on, and then you could simulate that directly, like ISMRD is maybe done, right? So in principle, Pulseq is kind of this, right? If you think of model-based reconstruction or so, right, then simulation and reconstruction become very similar problems, right? So you need to know more about the dynamics and everything. And in a way, I think case-based data is not enough. And in the future, the sequence somehow has to be in the raw data somehow, right? And Pulseq together with MRD is exactly this. Yeah? And I don't know if the vendors have something like that, but that's something that we have, and that's great.
If I may add a little bit, we happen to have submitted an abstract together with Martin Feldman from Bonn. I just pasted the link to the tool which produces a Pulseq file from the IDEA simulation file. So on Siemens, whatever you can simulate in IDEA, you can convert back to Pulseq and then feed into any simulation tool, or also run some other scanners. So I'm a little bit worried that we are letting a gin out of the bottle here. So we'll see, but we'll see what happens. At least there is this tool out, and another point is that some smaller vendors like a Neoscan from Magdeburg, they actually have native Pulseq export for exactly that reason. So they like to have interoperability. They don't feel protected, so they can export any in-house sequence into Pulseq and play it out on other hardware or simulate them. So I think we have to convince the traditional vendors to follow.
I think so too. That's great, Maxime. Yeah, and one way to think about it is it's sort of like you could, when developing the sequence, use that as your QC target, right? Use the vendor converted sequence, which maybe has more, I don't know,
Bells and whistles.
wouldn't be exactly the same, but also would be a possible target for optimization and things like that.
Yeah. Whereas one thing, of course, with open is, once again, I really have to warn everybody on the call: please don't copy vendor sequences. So, the way for us to get ourselves as a community in trouble is to start replicating copyrighted material and just publishing it on open source. That's a slippery way. So, publish your own stuff, publish your ideas. Don't try not to replicate one-to-one whatever you get under an NDA or anything, because that's something we should be careful with.
All right, I think we should move on. So thanks so much. That was
Thank you.
good.
Oh, well, I have one more question. I actually had a question to Christoph and Patrick. Do you want us to link your tools on harmonized MRI or on Pulseq, whatever? I think everybody would benefit from more publicity and transparency.
Definitely, yeah. Yes, please, yeah.
I think that's
Okay.
great.
The easiest is actually if you go to the website and submit the form, you can upload a logo, and then the rest is pretty automated. So
Perfect. Yeah, we'll do that. Yeah. Thanks.
thanks so much.
Yeah. Great. Thank you.
All right. So yeah. So Rita and Amir, if you could introduce yourselves and take it away.
Okay, so I will just share my screen. Do you see the presentation?
Yes.
Okay. Okay, so I'm Rita Schmidt from Weizmann Institute of Science, and I will tell you about my lab Pulseq projects. I will start, and then Amir Seginer, who is a staff scientist in our MRI center, will tell a bit more about details of the implementation. So my lab is interested in developing methods to improve brain functional studies, working with 7 Tesla MRI. So we have studies where we are working on fast or high tempo resolution projects involved with API sequences. And on the other hand, we have topics that also involve quantitative biomarkers, where one of the projects are T2 mapping based on a specific partially spoiled GRE sequence. And so this is how we started our Pulseq project. So first project, which is on the harmonized side, is a project where we wanted to eliminate or reduce artifacts due to physiological fluctuations. And so in this context, we work on 3D GRE sequences, and here are some examples of those types of artifacts. On a kind of a common T2 star weighted GRE, you can see those type of stripes due to vessels artifacts. So this is due to cardiac frequencies. You can see here some stripes in the middle of the brainstem. And there are also eye fluid fluctuations that are not exactly periodic, but there's some periodicity in it. And you see another, so on the right, you see an example from our T2 mapping related GRE acquisition, where this cardiac pulsation comes as an artifact from the ventricles. And on the bottom, you see examples of an example for time of flight angiography. So there are many stripes. So in order to remove them, to make the story very short, we came up with an idea of local scrambling or shuffling the order of the acquisition, which we can define in a specific window of shuffling that it will define a cutoff frequency. We'll see at the bottom figures that slow frequencies will stay untouched, while fast frequencies, we will smear them out. And on the right, you see a figure of the artifact intensity as function of frequency, and the blue plot shows the artifact intensity for Cartesian order. And we examine several different acquisition orders, and in the green is the one that we came up with this local scrambling approach. So you can see here examples where again now we scanned with ordered and with our local scrambling, and we removed or reduced significantly those types of artifacts in different 3D GRE based sequences. On the right, you see a MIP for time of flight acquisition. And recently, this is not Pulseq, but we also have a recently collaboration with Neurospin 11.7 Tesla, where they acquired 400 microns resolution GRE acquisition, where also now it becomes even more important to remove those local artifacts. So here on the left, you see the artifact, and with our local scrambling, we removed it. So this we wanted to be able to share and also to test all kinds of trajectories, and this was our first Pulseq project. So we implemented 3D GRE with all kinds of basic parameters to control, like slab selection or non-selective RF pulses, like what is the RF spoiling, specific properties, multi-echo, spoiler direction magnitude, and also on scanner reconstruction. This is for Siemens only. And on trajectories, and we implemented in this sequence several trajectories and order variants. So the Cartesian, which is the basic one, there are 3 spiral-like center out order. We implemented an example of semi-randomized acquisition based on Hilbert, generalized Hilbert space filling curve, a full randomization, local scrambling, which can come with combinations. You can see at the bottom those plots of the acquisition orders that we can, for different trajectories, add this local scrambling option. So now, in very short, moving on to another project that we are now working on. This is where we are working on EPI implementation with Pulseq, where we show that we can reduce acoustic sound and also ghost artifact by adding very small time delays in the API sequence. So the idea is that we came up with a model that can predict or model the acoustic spectrum of a specific API set of parameters, given the echo spacing of the echo train and the number of echoes in a multi-echo, number of slices, and so on. And here you can see an example. In red is the acoustic spectrum of a specific set of parameters. But what we found out that just by tiny changes of the timing, here an example of just by 0.4 millisecond change of the time delay of the time between echo or between slices, we can totally change the acoustic spectrum distribution of this of our API. Now, which of them is better? It actually depends on the transfer function of the specific gradient system. And so now we can also measure the transfer function and predict what will be the acoustics. And so we implemented, again, we started from implementing this in IDEA, but now we also implement in Pulseq, a multi-echo, multi-slice API, when we actually can control all those small timing delays. So what you see here, an example of the sequence diagram of API. So we can change the timing between slices. And for example, we can change the timing, exact time of the navigator, very small changes in the timing. And we can actually do it in a sweep over a range of parameters in the same scan. So changing the timing, changing the echo spacing, switching specific gradient blocks. Some of the scan make them just quiet, just without any gradients and so on. And now we can examine different API parameters. Here you can see some examples of different echo spacings. And then again, we sweep the maps show the acoustic power as a function of the timing between echoes and timing between slices. And again, the message here is to show that we can simulate and we measure corresponding very similar patterns as we simulate, and we can achieve significant differences between or reduce the acoustics by factor 5 to factor 50, depending on the parameters of the specific scan. So now Amir will tell a bit more about the details.
So as Rita mentioned, the 3D Scrambled GRE was our first Pulseq project, and we had several goals. First, to be flexible without any hard-coded parameters, and to support arbitrary 2D Cartesian trajectories, both current trajectories and possible future ones. We also wanted to automatically reconstruct in our Siemens system, so we won't have to deal with reconstruction, especially parallel imaging. Finally, we wanted a self-contained code independent of others, except of course for the Pulseq MATLAB implementation. We wrote more or less from scratch with inspiration from previous codes we found. This was a good way to learn, and instead of following others' unintuitive way of doing things, we did it in our own unintuitive way. I won't go much into the MATLAB code, but our project includes a main script and 3 subfolders whose functions are called as you would call a member of a class. The main script, the shuffle 3D GRE, calls Pulseq functions to create the .seq file with all the configuration parameters at its top. Here you can see an excerpt from it. The plus ordering folder holds different 2D ordering functions. To use a given scheme, you just have to set an appropriate function handle in the main script. Thus, it should be simple to add your own ordering scheme. You just have to be sure the functions input and output adhere to the expected format. Next, we have a system folder. It holds functions defining your system limits. So you should choose the correct system in the main script. The function can actually return several systems, each with a different gradient limitations, amplitude, and slew rate. So in the script, you can use different limitations for different blocks of the sequence. In Siemens lingo, this is fast, noble, and whisper, but you can define your own versions. Finally, there is the service folder, which holds miscellaneous functions. Currently just includes a function to update the definition section of the .seq, writing some definitions explicitly and some as comments. In some cases, we notice it confuses the interpreter if we write the definition explicitly. As I mentioned earlier, we wrote the code almost from scratch, which was a good way to learn. We developed this for Pulseq version 1.4.3. We had some issues on the way, and I must say Professor Zaitsev and his team, Dr. Chen, were very responsive. We did patch our local copy of the interpreter. The first patch overcame some crashes we had. I'm not sure the correction was the true cause, but after patching, we had no more crashes. I had a short email exchange with Professor Zaitsev, but I'm not sure where things stand now. The second patch was made to get parallel imaging to work automatically. Slam line counter labels were set incorrectly by the interpreter for some of our trajectories. I think this is now resolved in newer versions of the interpreter. Even with this patch, automatic reconstruction supports only 1D parallel imaging along the phase encoding directions. If you do not have the patch or want to do 2D parallel imaging, you have to patch the headers of the raw data using Siemens XBuilder executable and later perform what Siemens calls retro recon. We given our GitHub page there are instructions for that. Again, this is Siemens specific, I'm sorry. To conclude, we're pretty happy with Pulseq as it allows us to share our results. I do have a feature request for the interpreter. It would be nice to be able to choose an arbitrary reconstruction, including a post-processing one. Specifically, at the moment, we would like to get mosaic images for our EPR project and don't want to cannibalize an existing ICE. I would also like to be able to call system executables from Pulseq to run something in parallel to the sequence. In our case, to start an audio recording. So thank you.
Thanks so much. Questions or comments?
This looks like it's a good challenge for the phase view ordering. Was that what the issue was with the interpreter? That it was which ones worked and which ones didn't on the Siemens Pulseq?
You mean the
Or is the challenge at the passing to the ICE reconstruction?
So I think I mean, again, I think it might be specific to the version I used, the 1.4.3, but Pulseq automatically, the interpreter automatically puts some of the labels, but it tries to do that sort of intelligently because you sometimes skip And since we do our own sort of sometimes chaotic, it sometimes confuses the interpreter, and it says, "Oh, this is the first line, and not this is the first line we acquire, not the other." So, but I think they changed this logic behind it. I'm not sure we tested it with a new version, but
I wonder if you managed to break the current code, because it should be able to figure out real, true first and true last. The previous one was just a set of hex.
Yeah.
Based on the experience, but we tried to do it properly, basically to figure out, when the data starts and keep track, when the data ends, when the slices start, when the slices end. But it's of course, whatever you do, we try to learn from what you think is reasonable, and then somebody comes up with a new great idea.
Sorry.
That's fine.
It's a good challenging phase ordering.
It's fun.
I have a quick question. I'm really glad to see you're working on acoustic modeling, because I think that's something that at least as far as I can tell, it's harder to get open implementations of, and the vendor implementations seem more opaque than, let's say, the PNS models that they use, which we actually have open source for. Maybe you said it, to build your acoustic prediction model, was that based on physical measurements then of the scanner? How did you?
So it's Amir will maybe answer in a minute more detail, but the idea is a combination. So Amir wrote kind of a mathematical representation, but this is one part. But another part is the transfer function. So the transfer function we measure, and then we combine those two parts. There's kind of a theoretical model that takes into account specific all the timing of the acquisition, and then transfer function we measure, and the combined output is the acoustic power that we expect to get.
And what's involved in the transfer function measurement? Like, is there a particular protocol you followed, or what are if we wanted to do this ourselves, like what are the issues?
So initially we did the sort of what was to us naive. We just took our sequence, left just the readout gradients, which are in our model, and then compared to the recording and divided one by the other and got the transfer function. But now what we do is actually we have a Pulseq sequence which just does the triangles. But I don't remember the details, but let's say a few milliseconds apart from each other, and then so that because it's a short triangle, it has a sort of a large bandwidth for the acoustics, so it does about, I don't think, 4,000, 5,000 hertz until you get to a null. And then we repeat it, I don't know, a few seconds. But because the triangles are far apart, then we get our sequence is our spectrum has the time it sort of has a delta functions which are very relatively far away. Again, I don't remember exactly the details now, but so we wanted to shift these delta functions. So we had them, let's say, I'm just throwing a number, let's say every 10 hertz, and we wanted them every 1 hertz to have data in our spectrum, an acoustic spectrum. So from, in fMRI, if you do a linear phase, you get a shift, right? After you do the FFT. But we couldn't do a linear phase, so we just did like you do. So we just did a sine envelope, and that's sort of the addition of one linear phase one way and a linear phase the other way, and that's how we fill our spectrum in the middle. So we have I think we now have I think it's a 6-minute sequence that does 10 averages, but I think you can cut it down to 3 or even 2 averages, which cuts down the time, and it looks pretty good. I know other people do, so on the system. There are people who do sort of, the Siemens service sequences do either the sweep of the frequency, or they do a random noise, sort of random gradient, and then it's a white noise, and do FFT of that. We were warned that if you do not change the parameters there, you might break your gradients. So I'm just not even trying it, although I know other people have tried it and used it. So, but I'm trying to stay away from those sequences.
Yeah, so I just will comment. So Amir did really this implementation. What the main goal was to run a scan that with relatively low gradient amplitudes, and supposed to be, I think, no chance that we'll have any damage to the scanner with this type of sequence. This was one goal. And now that we have it, I think it has a relatively good quality of like the measurement of the transfer function. Usually those kind of sweeps are relatively noisy, and Amir's results are relatively good. And actually, this may be a good platform to tell about it, because it will be really interesting to measure it in different sites. This is something that we would be really glad to do, because we have on our side a lot of questions of when this transfer function changes. So we now kind of collect all kind of over time how the acoustics changes and so on. So if somebody wants to measure and tell us how it looks on his system, it will be interesting to do.
Well, I think that's a great suggestion.
Which kind of audio hardware do you use to record the sound? Do you need a special microphone which can go into the MR?
So we have optoacoustics, yeah, but we did it. So we actually scanned in CMRR now and in Neuroscreen with another so. From our point of you can do it in any format, and we will so of course you need the acoustic recording device, but otherwise we kind of already support different formats to read it and in order to analyze it.
Very good.
Maybe one quick question. So in the physiological type correction to the sequence, that was sort of scrambling or spread spectruming the artifact, but it wasn't clear when we're talking about avoiding the resonance. It seems like you were selecting just different fixed changes to the delays. So there's still a resonant frequency, but you were just avoiding, I mean, there was still a kind of a fixed frequency that the sequence was running, but you were avoiding the specific resonances in the system. Was
so
that
what
true?
we did is we didn't avoid, we minimized the acoustic power. So taking into account the specific frequencies in the transfer function will have higher intensity. This one we will try to reduce these specific peaks, but kind of we do it not by checking specific frequencies, but just overall acoustic searching for a case that of the timing that the overall acoustic power will be minimal.
I think,
but it was, I guess what I was asking was, it's still a fixed period or in the sequence, it's not jittering or scrambling, spread spectrum.
Yeah, exactly. So
modulate.
in this sequence, it is exactly the same API sequence, but instead of when you choose your TR, okay, so and inside the TR, the slices are usually spread uniformly. Right? So instead of so you maybe reduce a bit the actual overall time, or reduce or increase the overall TR in the case of the multi-slice. Okay.
I think I
But
understand.
again, the changes are very small.
Interesting. So just from my understanding, but for that, do you have an idea how long is the time when your mechanical oscillation of the gradient actually survives? Do you have a rough estimate or a Q factor of the gradient? Because
the rule of thumb I use, and I think it's not entirely correct, just looking at the recording, I'd say 50 milliseconds is about when it sort of
dies off.
Decays off. So maybe it's 100, but that's order of magnitude.
Yeah.
Okay, so then I understand. It makes sense that, for example, your neighboring slices are played out in antiphase, so the next slice would suppress the previous resonance. Okay, I see.
So yes and no, but at the end, because at the end it depends. So again, if you didn't have a transfer function, it doesn't matter how you change things. You're saying you still have the same, Parseval theorem. You still have the same energy. That's if you don't have a transfer function. But if you do have a transfer function, then it does matter where the peaks land, and then that's what's important. So it could be that you have to antiphase. It could be not.
But
it depends on the phase and the evolution and everything, right? So, but yeah, it's.
Yeah, but the whole point that we discovered that, well, everything happened because of all of the acceleration that we are using nowadays, that our ecotrains are usually can be shorter than this time that you asked about. So we can have ecotrains of 20 milliseconds, right? And therefore there is an interaction between the ecotrains of the slices and so on. And this is where this timing becomes very significant.
And did you my understanding that the mechanical resonance of the gradient is also something which contributes to the ghosting artifacts? So do you see a change in the ghosting? Does it get better or worse if it's generally gets quieter, or is there any correlation there?
So we thought at the beginning that it is correlated, but eventually what we actually saw that what is correlated is this the correlation to the frequencies. But what is important to the navigator is that kind of the navigator will feel the same acoustics as the acquisition. And so what actually important to reduce the ghost is the navigator, to shift the navigator a bit. But we clearly see a correlation to the acoustics. So we have our special example where we actually choose a case where the acoustics, the highest peaks are actually due to the third harmonic. And we saw that also the ghosts are behaving in correlation to the third harmonic. So this is how we know that, everything is related, but it's not that. So, or let's say differently, we can choose the minimal acoustics case, the quietest case, and we still can, for this case, find optimal ghost properties, optimal navigator location where the ghost will be minimized. So,
interesting. Okay, so it's related, but not directly.
Yeah.
Okay.
Very interesting. So we are over time. So I would think we should just wrap it up.
Yeah. Also, please consider sharing it, right? So it's great work. Sounds very interesting.
We're working on
it. If future speakers, please volunteer and share the information, the website, with anyone who wants to take part in this.
I think in January we still have the one slot free, or is it taken already by now?
It was at the beginning of the meeting. It was free.
Okay.
Yeah. So the one
So-
free, and then we haven't scheduled February meetings and so forth. So hopefully we can keep this going. But I'm learning a lot. I'm loving it. So hope it's useful.
Okay. Yeah. Please volunteer. Otherwise, enjoy the holidays. Even if you don't celebrate, just enjoy the long weekend.
Mhm.
Thanks, everyone.
Right.
Take care.
Take
Bye
care,
bye.
everyone.
Thank you. Bye, everyone.
Bye bye.
Bye.